Good afternoon. My name is Maksym Kizitskyi, and the topic of my today's presentation is a modular approach to enhancing safety in text-to-image diffusion models via targeted LoRa fine-tuning. Text-to-image generation models, like Stable Diffusion, are increasingly used in design, media, and education. However, these models can also generate harmful or inappropriate content, especially when exposed to prompt attacks. Existing safety mechanism often fails in these edge cases or compromise image quality. Our work addresses challenges by proposing LoRa-based safety framework. This is modular, scalable, and capable of fine-tuning for specific harmful categories. Approach, which will provide both uh, robust protection against different types of threats while maintaining image quality. The aim and goals of this work. The primary aim of this study is to enhance the safety of text-to-image models by reducing their vulnerability to harmful content generation. To achieve these goals, we develop a fine-tuning strategy based on low-rank adaptation combined with metric learning. Our goals were to create and evaluate a general LoRa adapter for overall safety implementation, train targeted adapter for specific harm categories such as self-harm, test our methods on advertisal datasets, and compare the results against baseline and industry benchmarks to ensure we maintain both safety and generation performance. In order to evaluate our model, we choose two datasets. First one is advertisal Nibbler dataset that contains over 3,000 data crowdsourced prompts for text-to-image models and contains different types of prompts from direct advertisal prompts to hidden mm, manipulations of model outputs and so on. The second one is I2P dataset. It contains over 4,000 real-world prompts, and the prompts are split into 7 categories such as self-harm, hate, violence, etc. You can see the distribution of each class on the plot on this slide. Also, the dataset considers toxicity rating, but it was not used during this research. As a key metrics, we've chosen attack success rate, which basically measures what percentage of prompts of advertisal prompts were successful into creating harmful or inappropriate output. Next one is NSFW score. We considered minimal, maximum, and average. Uh, that this matrix showcases what is the score an automatic classification model based on visual transformers gave to image. And the logic behind this metric was the lower the number is, the less likely image to be as the less likely on the image it will be some inappropriate content. Also, because no, the classification model is not perfect, we also performed some visual assessment on some edge cases. For experiment, we chose the Stable Diffusion 3.5 medium because it's one of the most advanced open source models nowadays, and performed several experiments. First one is to evaluate model on collected dataset with advertisal prompts without any protection mechanisms. It was our baseline, after which we decided to implement our protection mechanisms. Next one, we trained a general mm, purpose LoRa adapter. We trained it on all harmful content categories with subcenter arc phase loss function. Our goal was to move the latent representation of harmful prompts far away from not harmful ones. That is why model will generate only not harmful outputs. And last experiment was to train a specific LoRa adapter for some category. We've chosen a self-harm to see if it's possible and if it would be any better to train adapter not on all categories but on some specific. For each prompt we've generated 5 images and on each one we perform classification of the model mentioned before. And for some edge cases, when the model was not sure, we performed manual inspection of images. On this slide, we can see how the training process was for both experiment 2 is general purpose LoRa and experiment 3 is LoRa for one specific category. As we can see that loss on training data set for both loss functions was pretty fast, but for one specific category it was way better. And in the end it reached way lower value of a loss function. So let's proceed to our testing results. On this slide you can see how both models performed with attack success rate. So base model achieved attack success rate of 31%. That is actually pretty much. So basically every third image of advertisal prompts was harmful. While with implemented general purpose LoRa, it reduced to 16%, which is really much decrease. On the other plot, we can see how that model with one specific category of LoRa trained for specific category achieved even lower results, 8%. So, as we can see from the slides, that training LoRa for one category is more beneficial. As was shown from previous slide, LoRa-based fine-tuning significantly reduced the harmful outputs while preserving the image quality. General adapter achieved 48% ASR reduction, and specific adapter for self-harm achieved 74 reduction. That is pretty impressive. Category-specific adapter demonstrate better visual quality than a general list filter. That's why it is shown that it would be pretty prominent to scale adapters not to all the topics and block them at the same time, but to use specific LoRa for specific use case. Also, based on previous slides, that after 7th epoch, training reached a plateau. It could be performed because it could happen because of lack of training data or model capacity. Also, the future validation need to be across other harmful topics and different models, not only stable diffusion 3.5 medium. And also, white box advertiser testing is essential for evaluating and long-term robustness. So this approach should be tested against advertisal prompting. So, in conclusion, in this research, we proposed a modular safety framework using LoRa fine-tuning and metric learning for testing text-to-image models. The approach effectively reduces the harmful outputs while maintaining image quality. Class-specific adapters, in our case self-harm, outperform general filters in both safety and image quality, achieved safety performance compared to industry benchmarks as safe, stable diffusion. The method is scalable, resource efficient, and adaptable to multiple harm categories. Further work includes broader testing, cultural adaptation, and resistance to white box advertisal attacks. That everything. Thank you for your attention.